Okay, morning everyone. Numbers are sort of stabilizing, so let's make a start. So thanks for coming along to today's webinar. We've got another one of our sort of early career researcher double headers. First up is going to be Sosuke Inui, who's a postgraduate student at Osaka City University in the group of Makoto Sabota, and he's going to be talking to us about finite temperature turbulence using a fully coupled model based on the lattice Boltzmann method. So Sosuke, when you're ready, please take it away.
Thank you very much. Thank you very much for giving me such a great opportunity to give a talk here. Today, I want to talk about lattice Boltzmann method based on, right. So let me, So today's content, what I'm thinking is something like this. First of all, let me briefly talk about the introduction background of this study, and I will show you very simple examples and a little involved examples, and I will summarize. Well, first of all, let me go ahead and start introduction part. So the study of superfluid helium has a long history, more than a half century, and there are many great experiments, but also there are several numerical studies, and numerical studies have also contributed significantly for better understanding of superfluid helium, especially for past few decades. And there are there are two major approaches for numerical study. Well, one is based on the individual vortex motion, such as the vortex filament model. And of course, there are studies based on macroscopic or coarse-grained quantities. The most famous one is like HVBK approach or HVBK equations. And there are recently several methods that solve the two-fleet coupled dynamics by coupling these two approaches. And they have opened up a new direction in the study of superfluid helium. And today what I want to introduce is like a kind of similar method, but we solve superfluidity using vortex filament model, and we solve lattice Boltzmann method in order to get the normal fluid dynamics. Well, idea of our numerical scheme is very simple. Instead of directly solving Navier-Stokes equation, we solve superfluid with vortex filament model, and we use lattice Boltzmann method for normal fluid. Well, and I want to talk a little bit on the computational scheme. Well, I assume today's audience here are pretty much familiar with the vortex filament model. So I will just give a very brief explanation on the vortex filament model. It is the computational model which was first developed by Schwartz around this year. Well, the concept is like take a vortex filament and discretize into points with direction and calculate the superfluid velocity at each point. And according to the equation motion given something like this, we calculate the next point of the vortex points. Well, because of the time constraint, I just for the normal fluid, we use lattice Boltzmann method. Probably this method is not that familiar in this, especially this in the superfluid community. So I want to say a little bit more in detail. Well, this lattice Boltzmann method is a widely used method in classical fluid dynamics community, which lattice Boltzmann method solves indirectly the Navier-Stokes equation with second order accuracy in space and also in time by simulating streaming and collision among mesoscopic fluid particles. And at each lattice site, we discretize momentum or velocity into Q states. Well, in this talk, in this study, we are using like 3D, so-called 3D Q19 lattice. Well, basically we have three-dimensional space and 19 different velocity sets. And what we are gonna do is evaluate the density distribution. For example, for ith momentum state, pick one, and the population there is, and we calculate two populations. One is at the equilibrium and also at the non-equilibrium. And what we are going to do in this scheme is to follow the population density. In usual classical dynamics, we often use momentum for this guy, but in here for the later convenience, we use velocity here. So we are going to follow the time evolution of this guy. So what we are going to do is take derivative. And because of the chain rule, we have three different terms. And we are going to equate this whole thing with an source term, which is often called collision integral. In general, this is very complicated form, but this whole thing is so-called Boltzmann equation. Well, in lattice Boltzmann method, we are gonna make many approximations, and we are gonna approximate this collision integral. And one of the most powerful and often used collision operator is so-called Bartnagar-Gross-Krug collision operator, and look like this. Well, what it says is like the collisions take place proportional to the difference between two populations, and they tend to go equilibrate. And this tau is so-called relaxation time, which is related to the viscosity of the system. Well, so this is the lattice Boltzmann method. And the way to implement this model in simulation is very simple. We just need to have like 3 steps. Step one is to calculate the equilibrium population density at each lattice site. Well, if we believe the local equilibrium hypothesis, then the distribution would look like this. But we will make it discretized into these spaces, and we are gonna calculate this thing at each site. And what we are gonna do next is calculate the collision integral in the previous equation, and we are gonna make this guy operate on the population itself, and we call this thing as post-collision population. And for the final step, what we do is stream these particles to the next neighboring site. So F star is the post-collision operator, and this is gonna be the next population. Okay, so this is very simple. And probably many of you guys think like why this guy is able to Navier-Stokes equation, why lattice Boltzmann can simulate the Navier-Stokes equation. The short answer is because this model, or using this model, the continuity equation and Navier-Stokes equation can be rigorously derived from the lattice Boltzmann equation with BGK collision operator we saw earlier. So what we will have is continuity equation of this form and this form. This is same as the classical fluid dynamics. And but there is a difference here because of the truncation of higher moments. And so this scheme is often said like only valid for low Mach number cases. And this is the last slide for the computational aspect. Well, the treatment of vortex filament, the interaction between superfluid and the vortex filament and the normal fluid. Well, we take the most simple scenario. Well, this is a force on the vortex filament for unit length. So the force, the mutual friction force is acting on this point here, let's say. Then we have to interpret this force into 4 neighboring points. And we are gonna translate into body force density. Then we couple these two dynamics. Okay, so this is the concept of simulation. Of course, there are pros and cons for lattice Boltzmann method. For the pros, what I want to mention is that this model is mesoscopic model, so interaction with vortex filaments are rather simple than using Navier-Stokes equation. And also complicated boundary condition may be a little bit handled easier. For example, these spherical situations. And also for the pros, I want to say that this simulation only contains linear and local operations, so much easier than Navier-Stokes. For the cons, I want to say that in order to make the simulation very high resoluted, it requires high computational cost. So it could be troublesome. And also simplest implementation of this model contains an error term of U cube that I talked about earlier. In today's so in today's talk, what I want to tell is that our numerical scheme based on these computations do reproduce flow structures known in previous studies and also reproduces T1 turbulence regime under thermal counterflow in a channel. And I want to say a little bit on the quantized vortices near the wall of a heater. And this section is very short. And so this simulation shows a vortex ring in black and 2 isosurfaces, normal fluid. These isosurfaces, isovorticity surfaces, and parameters are given like this. And we can clearly see the so-called 3 vortex structure first proposed in this paper here. And what we can say from this simulation is that by comparing this result with the conventional VFM simulation, we would get something like this. So blue one is only VFM and the red one is our new computation. And it clearly shows that the vortex ring lifetime is elongated by coupling the normal fluid. We can interpret this as quantized vortex drags normal fluid component around it, and the relative velocity between these two components decreases, and therefore the lifetime of the ring increases. And I'd like to show you a little bit more examples, reconnections. So these are 2 typical reconnections, ring-ring collision and line-line reconnection. So in this, at the reconnection, it is known that there is a dynamic scaling. So the closest distance between 2 vortices is proportional to square root of kappa and time. And this can be clearly observed in our simulation as well. This the vertical axis is basically A. So before the collision, it stays constant, and after the reconnection, it jumps, but it stays constant. So we can clearly see that the coupling with normal fluid doesn't change the scaling behavior. Okay, And I want to show you a little bit involved examples. Well, this simulation is motivated by a recent experiment by Mastracci et al. In Florida State University. And they observed anisotropic fluctuation in normal fluid profile in thermal counterflow. And recently, Yui et al. Gave a simulation based on Navier-Stokes equation with parameter like given here. And we try to reproduce their result. And the result is this. And as those two groups obtained, we can see the anisotropic fluctuation in these simulations. And if we plot the fluctuation in x direction, so flow direction and perpendicular directions, we could obtain something like this. And this quantitatively agrees with the result obtained by Yui et al. And also we could calculate the vortex line density as a vortex line density as functions of time. So it clearly saturates to some value, and from the saturated value, we can obtain the proportionality constant gamma. The value we obtained was something like this. This value also agrees with the value obtained by Yui et al. Within the margin of error. So, and I want to say a little bit more. Well, I want to talk about the possibilities of lattice Boltzmann-based approach. Well, in the previous case, we had a periodic boundary condition in the streaming direction. So this wall and this wall were periodic in the previous slide, but this time they are a solid boundary as a heater. So there is normal fluid coming out and superfluid coming in to this wall. And if we run the simulation, we could see something like this. So at the glance, before running the simulation, one would guess that all the vortices would be sucked in the wall, but actually we have a statistically steady state like this after some time. And if we take average of all the vortex configuration after this time on, we could obtain something like this. So this horizontal axis is the distance from the wall. So we clearly see a inhomogeneous vortex angle, which could be related to the thermal boundary layer, which was discussed, for example, this paper, recent paper. So this is actually the almost the last slide. So so today I talked about our new computational scheme for simulating two-fluid dynamics based on the lattice Boltzmann method and vortex fragment model. And our numerical simulations do reproduce flow structures known in the previous studies. And we were able to reproduce the T1 turbulence regime in thermal counterflow. And we discussed about the possibility to study the behavior of thermal boundary layer near the wall of a heater in thermal counterflow. And I want to discuss a little bit about the thermal boundary layer. So we are now able to calculate the vortex line density, and we know the property of the statistical steady vortex tangle. Well, this is vortex line density and the relative velocity between super and normal fluid. And that is related to the gradient of the temperature, especially for the normal the vortices. So we can in principle, will obtain the local temperature of the vortex tangle. So if we reapply this temperature into the vortices in these tangles, then we may be able to say, like, we are able to understand the Kibble-Zurek experiment in superfluid helium in a more quantitative way. And I want to say one more thing. So in this approach, this model is based on two-fluid model, where superfluid velocity and normal fluid velocity are equally important. They are the key quantities. But we only took normal fluid velocity and converted into Boltzmann equation, and we discretized into a thermal lattice Boltzmann method. But recently I'm thinking if we could do something like this, if we take two-fluid extended model or one-fluid extended model presented in, for example, this paper, this model is based on barycentric velocity and heat flux. So I'm wondering if we can take this guy together and convert it into Boltzmann equation and like discretize this into thermal lattice Boltzmann method. So, but if we could do this, it could be very useful to get this kind of thermal behavior of quantized vortices. But so this is what I'm thinking recently, but I want to hear your opinion though. So this is basically my last slide. Thank you very much for your attention.
Thanks very much, Sosuke, for a very interesting talk. Any questions, feel free to raise your hand, unmute yourself, or pop a question in the chat and I can read it out. While we're waiting for the people, I was just a bit unsure, what with the final simulations with the heater,
yes.
What do you do with it? Do you assume a fixed temperature along the channel, and then the final part that you were showing was trying to later?
One, yes.
So the temperature is assumed to be fixed along the channel, but then,
right?
Because you would imagine in reality you've got some profile of the temperature that's higher near the heater, and obviously you can't simulate easily above T lambda. But then the second part, you were trying to back out an effective temperature. Is this something that you're trying to dynamically change?
You mean this one?
Mm-hmm.
So yeah, this is what I want to do in the. I haven't done this yet, but I want to do this in future works, because yeah, near the heater there is definitely temperature gradient, but there is no way to feed back the temperature. Like, so what I want to do is, like, assuming the normal fluid temperature stays the same, but change the temperature for the vortices according to the density profile. That's it.
Okay. Yeah, I think I understand. And there's a question in the chat from Andrea Berezi. I probably missed it at the beginning, but is this concerning the BEC regime?
Not really. So what is I'm using Boltzmann model, but it's not necessarily dilute. Well, because of the so although I'm using Boltzmann method, it's not necessarily dilute. Like this lattice Boltzmann method solves Navier-Stokes equation with second order accuracy. So it's not necessarily BC regime. You mean like the normal fluid is very, there are a lot of like, the normal fluid is hydrodynamical thing. Am I answering that question?
Yeah, I think that's cleared it up. And time for a really quick question. Gabrielle, you've got your hand raised. Please just.
Yes. So what are the free parameters in your model that you need to set before simulation? And how do you select values of these parameters? I mean, you take it from some other calculations or you fit it to the experiment?
Right. I use these parameters so that I can compare with the result obtained by Yui et al. Like recent couple dynamic simulation based on Navier-Stokes equation, and they solved like they right. These parameters are pretty much the same, and also so I try to see, try to reproduce their result. So I pick the parameters so that our results match theirs.
So in total, how many parameters do you have in your model?
No, model. Well, let me. So we can tune the viscosity of the normal fluid and the that, of course, the vortices or temperature is also a parameter that we can tune. And the other parameters. What I can think of just now is just the viscosity and the or relaxation time, or and the temperature. That's it. And actually, there is a the modeling. The lattice Boltzmann approach actually contains one more. It has a sound velocity kind of like unique to this model, and that could be so if we as I told you earlier, like in the slide, there is this approach only works at the low Mach number because this approach can't solve for high velocity regime. So like that parameter, Mach number could be also a parameter. Am I answering your question? Sorry.
Thank you.
There is one more question in the chat. In the interest of time, I just wondered if maybe you could answer that one, Sosuke, and but take your slides down, and we can get Matt up, and then.
Could you continue with Felix? Right, could be, but in my current implementation, this is not doable, but the free surface, right? The interaction between vortex and the surface would be very interesting. And yeah, in lattice Boltzmann method, the treatment of surface may be easier than like solving Navier-Stokes equation, but there are many issues that we need to think about if we want to do this simulation. I want to do this. Am I answering the